Hello viewers, question 3. In this question you will investigate the ballistics pendulum. This is a relatively low-tech way of determining the speed of a bullet. A bullet is fired into a block of wood on the end of a piece of string. From the height the block swings to, we can calculate the speed of the bullet. For this question, the mass of the bullet is 4 grams. The mass of the wooden block is 3 kilograms. It is observed that the block swings to a height of 9 centimeters after the bullet is fired. So let's draw a sketch of the situation. We've got a 3 kilogram wooden block hanging off the end of a piece of string. A bullet is fired in and hits the end of it and sticks into the block. As it does so, the block is going to swing upwards, and at the top of its swing, we've got a height difference there of 9 centimeters. Now the bullet is also embedded in the block, so the mass of the whole block is now mass of the block plus mass of the bullet. 3 kilograms plus 4 grams is 3 kilograms plus 0.004 kilograms, which is 3.004 kilograms. Okay, so we've got information we need to determine the potential energy, because at the top of the swing, all of the kinetic energy that was given to the block by the impact of the bullet has been converted into potential. So for part A, we've got potential energy is mgh, which is mass is 3.004, because we're talking about the whole object, times 9.81 multiplied by the height difference is 0.09 meters, and if we calculate that, we end up with 2.632 joules. Okay, so that was question A. Now question B, we need to determine the kinetic energy of the block bullet immediately after the bullet embeds itself in the block. So as we just pointed out, the kinetic energy of the block bullet combination immediately after impact gets converted into potential energy on the upswing. So the amount of kinetic energy it has immediately after impact, before it actually starts to ascend, must be the same as the potential energy at the top of the swing. So that must also be 2.632 joules. Okay, so we've got the amount of kinetic energy immediately after impact. Now we can determine the speed of the bullet block immediately after impact, because we now know the amount of kinetic energy it has. EK is half mv squared, and if we solve that for v, we'll multiply that through by 2. So we've got 2ek equals mv squared. So if we divide that by m, we get 2ek over m equals v squared, and we'll take the square root of that to get v. So therefore v is the square root of 2 times kinetic energy is 2.632. Divide that by the mass, which will be, we're talking here about the whole object, the whole block bullet combination, so the mass is 3.004, and if we calculate that, we get 1.329 meters per second. Okay, so part D, recall its momentum, not kinetic energy that's conserved in a collision. Determine the momentum of the bullet block combination immediately after impact. So for part D, we need to use the momentum formula, which is m times v. The mass is, we're talking about the whole block bullet combination, which is 3.004 multiplied by the velocity we just found, 1.329, And if we calculate that, we get 3.993 kilograms meters per second. Okay, so we've got the amount of momentum immediately after impact. And from that, we're going to use conservation of momentum to work out the speed of the bullet before impact. Now, in part B of the question, we were using conservation of energy, but we were comparing energy to energy after the collision to energy after the collision. We were comparing the amount of energy it had 1 microsecond after the collision to what it had at the top of the swing, which it was obviously after the collision as well. But for part E, we're working out what the speed of the bullet was before impact. So we're looking at comparing a speed before impact with a speed after impact. Comparing what's happening before a collision to comparing what's happening after a collision. And in that collision, there would have been some energy lost on impact, which means energy is not conserved, but momentum is always conserved in a collision. And before impact, the whole block was stationary, which means that all of the momentum must come from the bullet because that's the only thing that's moving. So therefore, the momentum of the bullet before impact must be also 3.993 kilograms meter per second, because the conservation of momentum indicates that the momentum before is the same as the momentum after. Momentum after is just one object, which is the whole block bullet mangled into one object, whereas before the collision, all of the momentum was in the bullet because that's the only thing that was moving. So we've got m times v equals the momentum. We want to find the speed, so the speed is going to be the momentum divided by the mass, which is going to be 3.993 divided by mass. We're just looking at the mass of the bullet only now, because that's the only thing moving before collision. So that was 0.004 kilograms. And we find that we get a value of 998 meters per second. Okay, so now we can find the kinetic energy of the bullet before impact. So kinetic energy of the bullet is going to be, kinetic energy is half mv squared, which is a half times the mass is 0.004, and v we've just found to be 998 squared, which is 1993 joules. So we can see there's actually been quite a significant loss in energy. Before the impact, total energy, which was in the form of kinetic energy of the bullet, was almost 2000 joules, and on impact the amount of energy that is retained in the bullet block combination by kinetic energy, which later gets converted into potential energy, is down to only 2.6 joules. So it's quite a substantial loss in energy there. Now, what happened to that loss in energy? What happened to it? What kind of energy did it get converted to? So it would have got converted into heat and sound. You would certainly hear something as the bullet hit the block, possibly a spark or two, probably not significantly, certainly not as much as there was in the first question, because that would have been metal on metal, but now we're talking about metal on wood, which means any spark would be negligible, but most of the energy would be lost in the form of deformation of both the bullet and the block. So there would be deformation energy here. Okay, and part H. If the bullet is shot by a 1.5 kilogram gun, what is the recoil speed of the gun? So before the bullet gets fired by the gun, there is nothing moving. So the total momentum would be 0 because the momentum before would be 0. Now, what about the total momentum after? Would also have to be 0 by conservation of momentum. So therefore, the momentum of the bullet plus the momentum of the gun must be 0, and therefore the momentum of the bullet must be negative the momentum of the gun. So the momenta must be the same in size, but opposite in direction to make the sum 0. Momentum of the bullet we've already previously found to be 3.993 kilogram metre per second. We found that in part D of the question, equals minus the momentum of the gun. So the momentum of the gun is going to be the mass of the gun multiplied by the recoil speed of the gun. And it's that recoil speed of the gun that we need to find. So to get VG, that recoil speed, it's going to be 3.993, and we need to divide by the mass of the gun, which is 1.5, and that is in the opposite direction. And if we do that, we get a value of 2.66 metres per second. Okay, thanks for watching. Over and out.